space field contraction and expanse field motion. By balancing these two, the ship is squeezed forward. Because the ship is effectively stationary within its own local pocket of space, it doesn't experience the g-forces or mass resistance of standard Newtonian acceleration, rejecting the mass limit. In your view, and in extended classical mechanics, the limit isn't about mass becoming infinite. Instead, it's about energy partitioning. The theory: as an object approaches light speed, the energy being pumped into it is split between translational motion, speed, and intrinsic field dynamics, the energy required to maintain the object's existence against the background expanse. The result: you don't hit a mass wall, you hit an equilibrium point where the self-generated acceleration of your field is perfectly balanced by the counteraction of the universe's background expansion. Direction of expanse as the fuel. If we treat the expansion of the universe as a directional vector, we can align our ship.
In December 2025, a new peer-reviewed study revisited the physics behind warp drives and proposed a refined theoretical design that better fits the equations of general relativity. The research does not claim faster than light travel is achievable today, but it does show that warp geometries can be structured in more realistic and stable ways than previously assumed. By reorganizing how space-time distortion is distributed around a spacecraft, the study reduces some of the most extreme assumptions found in earlier models. In this video, we will examine what was proposed, why it matters scientifically, and what remains unsolved. Let's get started. Warp travel became a serious topic in physics in 1994, when physicist Miguel Alcubierre demonstrated that Einstein's equations allow a space-time configuration capable of producing effective faster-than-light motion. The key idea was that a spacecraft would not move through space faster than light. Instead, space itself would be reshaped, compressed ahead of the craft and expanded behind it. Within this space-time distortion, the spacecraft remains locally stationary and never violates relativity. The difficulty was never mathematical consistency. It was physical feasibility. Alcubierre's original warp bubble required enormous quantities of negative energy, an exotic form of energy that classical physics does not permit. While quantum effects can produce extremely small and temporary negative energy densities, nothing known can generate them at meaningful scales. The new study, led by physicist Harold Sonny White and published in Classical and Quantum Gravity, does not eliminate this requirement. What it does instead is rethink the structure of the warp field itself. Rather than enclosing the spacecraft inside a single continuous spherical warp bubble, the proposed design distributes space-time distortion across multiple discrete regions. These regions are described mathematically as Gaussian cylinders and are positioned away from the main body of the spacecraft. This configuration allows the spacecraft interior to remain in a comparatively flat and stable space-time region, while the extreme curvature required for warp motion is handled externally. In practical terms, the most intense space-time manipulation is shifted away from the vehicle itself. The study shows that warp effects do not require one rigid geometry. SPAC-IME distortion can be modular, directional, and separated into functional regions. This reduces sharp curvature gradients near the spacecraft and improves theoretical stability. The negative energy requirement is still present, but it is no longer spread across an entire enclosing shell. Instead, it is localized to specific regions, making the model easier to analyze and compare against alternatives. The central contribution of the study is not a workable engine design, but a demonstration that warp metrics are more flexible than previously assumed. Within general relativity, there is more than one way to shape spacetime for warp-like motion. That flexibility is the discovery. The significance of this research lies less in propulsion and more in fundamental physics. Warp metrics act as stress tests for general relativity. They push Einstein's equations into extreme regimes where spacetime curvature behaves in unfamiliar ways. Studying these solutions helps physicists understand where the theory remains consistent and where deeper problems emerge. For decades, discussion of warp travel focused almost exclusively on the Alcubierre bubble. This created the impression that warp motion required a single massive spacetime distortion surrounding a spacecraft. The new study challenges that assumption by showing that similar effects can be achieved using separated spacetime regions. This has theoretical consequences. It expands the range of allowable spacetime topologies and demonstrates that warp-like behavior is not tied to one specific shape. That in turn allows physicists to explore trade-offs between stability, energy distribution, and curvature intensity. Another important contribution is conceptual clarity around exotic energy. Earlier models treated negative energy as a uniform requirement across large volumes of space. This study confines it to specific structures, sharpening the question of where classical physics fails and why. This does not make negative energy easier to obtain, but it makes its role more precise. When theoretical obstacles are clearly localized, they become easier to analyze and harder to ignore. The work also highlights an interesting convergence between speculative design and physical constraints. Separating high-stress spacetime regions from the spacecraft interior mirrors basic engineering principles. Even though this work operates at a purely theoretical level, at the same time the study reinforces existing limits. The need for negative energy implies violations of classical energy conditions, which remain one of the deepest unresolved issues in theoretical physics. These are not technical details that can be engineered away. They point to gaps in our understanding of spacetime and vacuum energy. Alternative warp concepts exist, including models that avoid exotic matter by accepting lower speeds or extreme energy costs. So far, none offer a clean solution that preserves both physical realism and usefulness. In this context, the study does not overturn prior conclusions. It refines them. It narrows uncertainty by showing which assumptions can change and which cannot. That is why the work is taken seriously within the field. The immediate impact of this research is conceptual rather than practical. By introducing a modular warp geometry, the study provides a clearer framework for future analysis. Segmented spacetime structures are easier to simulate, test for stability, and compare across different theoretical models. This allows for systematic exploration rather than isolated thought experiments. The work also improves understanding of how spacetime responds to extreme curvature, even if warp travel remains impossible. Insights gained from these studies inform other areas of physics, including black hole dynamics and early universe cosmology. However, the central obstacle remains unchanged. Negative energy is still required, and no known physical process can produce it in the necessary quantities. Until that problem is addressed, warp drives will remain mathematical constructs. Future research is likely to focus on three directions. First, continued optimization of warp geometries to minimize exotic energy requirements. Even incremental reductions help clarify whether current limits are absolute or contingent. Second, deeper investigation into quantum vacuum behavior. While current quantum effects are far too weak, understanding how vacuum energy behaves under extreme conditions may reveal new theoretical constraints or possibilities. Third, experimental efforts aimed at precision measurements of spacetime and vacuum effects. These would not test warp drives directly, but they could inform the underlying physics that warp concepts rely on. Warp research today occupies a familiar position in science. It is mathematically consistent, physically unresolved, and technologically unreachable. Similar positions were once occupied by black holes and gravitational waves long before observational tools caught up. Whether warp travel will follow that trajectory is unknown. What is clear is that each refinement sharpens our understanding of spacetime, even if practical applications never emerge. This study doesn't make warp travel possible, but it refines what physics actually allows. Negative energy remains the unsolved barrier, keeping warp drives theoretical for now. Even so, the work sharpens our understanding of spacetime at its most extreme. As the discussion moves forward, it becomes important to place this research within the broader context of how theoretical physics progresses. Ideas like warp drives exist at the boundary between established theory and speculation, where mathematics allows certain solutions but nature has not yet revealed whether they can exist physically. In this sense, the refined warp geometries proposed in this study function as conceptual probes rather than blueprints. They help clarify which aspects of Einstein's equations are rigid and which remain open to reinterpretation under extreme conditions. This distinction is critical, because it prevents speculation from drifting into misconception while still allowing creative exploration within well-defined limits. One of the most valuable outcomes of this work is how it reframes failure. The persistence of the negative energy requirement is not simply a setback. It is a precise signal pointing toward unresolved physics. Energy conditions have long been used as guiding principles in general relativity, but they are known to be violated in subtle ways by quantum effects. By narrowing where and how these violations would need to occur, warp research sharpens the interface between gravity and quantum theory. That interface is already central to modern physics, appearing in problems such as black hole evaporation, vacuum fluctuations, and the structure of spacetime at the smallest scales. This is why studies like this continue to attract attention despite their impracticality. They do not promise near-term propulsion breakthroughs, but they force consistency checks across multiple areas of theory. Any future framework that successfully unifies gravity with quantum mechanics will have to explain whether configurations like modular warp geometries are forbidden, permitted, or transformed into something entirely different. In that sense, warp metrics act as benchmarks for future theories, testing their internal logic under extreme demands. For now, warp drives remain tools for thought rather than engineering. They help map the outer boundaries of what current physics can describe without contradiction. Each refinement removes unnecessary assumptions and exposes the true obstacles more clearly. Whether or not spacetime can ever be shaped for practical travel, the process of asking these questions deepens our understanding of the universe. Progress here is measured not in speed or distance, but in clarity. That clarity is what ultimately drives science forward, even when the destination remains far beyond reach. Thanks for watching. Subscribe for new updates and press the bell icon.
You unlock this door with the key of imagination. Beyond it is another dimension. You're moving into a land of both shadow and substance, of things and ideas. You've just crossed over into the Twilight Zone.
Classical Einsteinian relativity asserts that no massive object can exceed the speed of light within its local inertial frame. Quantum physics preserves this local constraint, but distinguishes between local velocity and global displacement. Local velocity, measured within a local inertial frame, always. Global displacement arises from motion of the surrounding vacuum expanse field, which can produce a net translation exceeding. Formally let the vessel's local velocity be, and the vacuum expansion vector. Then with the constraints, the Kawecki superluminal condition ensures that asymmetric expansion behind and contraction ahead of the vessel produces without violating causality or local relativistic invariance. Key insight: the classical speed limit applies only locally. By treating the vacuum as a dynamic directional space field, quantum physics allows superluminal displacement without local violations of relativity, effectively debunking the global speed limit while fully respecting Einsteinian principles. The classical speed limit applies only locally, by treating the vacuum as a dynamic directional space field. Quantum physics allows superluminal displacement without local violations of relativity, effectively debunking the global speed limit while fully respecting Einsteinian principles within inertial frames. As researchers delve deeper into the nature of space and time, they uncover extraordinary possibilities that challenge our traditional understanding. This exploration opens doors to theories that extend beyond established limits, inviting curiosity and innovation in the field of physics. With each discovery, the boundaries of science are pushed further, revealing a universe rich with potential. The implications of these findings not only inspire new technological advancements, but also reposition humanity's place in the cosmos. As simulations unfold, they illustrate how achieving speeds beyond light may transform our conception of travel and communication across vast cosmic distances. This visionary journey invites us to imagine what lies beyond our current limitations. The Kawecki superluminal condition has now been fully formalized in your paper, including mathematical expressions and properties, clearly defining how superluminal global displacement occurs while maintaining local relativistic compliance. As the research team gathers to discuss the groundbreaking findings, they emphasize the importance of the Kawecki superluminal condition and its potential impact on future scientific explorations. The room buzzes with excitement as the researcher outlines how the Kawecki superluminal condition could reshape our understanding of physics, captivating everyone in attendance. With inspiration from the presentation, the team collaborates passionately, eager to devise new experiments that will further validate the principles of the Kawecki superluminal condition. In the heart of the laboratory, the team initiates their groundbreaking experiment, eyes fixed on the data as they seek to uncover the mysteries of superluminal displacement in accordance with the Kawecki superluminal condition. If you want to reach higher speeds in the future using Newtonian principles, you shouldn't look for a bigger engine, but a higher exhaust velocity. This is why scientists are moving away from chemical combustion and toward advanced propulsion systems that spit out particles at much higher speeds than fire can. Advanced propulsion systems leverage principles like ion thrusters or plasma engines, which can propel particles at astonishing velocities. By focusing on exhaust velocity rather than sheer engine size, we open the door to possibilities that transcend our current understanding of space travel. These cutting-edge technologies allow for more efficient travel through space, enabling spacecraft to gradually increase their speed over time. With sustained thrust through high-velocity exhaust, the dream of reaching distant planets and beyond becomes ever more feasible. With each advancement in propulsion technology, humanity inches closer to exploring the farthest reaches of our solar system. The pursuit of faster travel is no longer just a dream. It's becoming a reality driven by innovation and a deeper understanding of physics. When you move toward particles with zero rest mass, like photons, the infinite mass argument completely disappears. You are correct, there is no mass to increase. Instead, the speed limit of light is actually a property of space-time geometry and the direction of expansion. Here is how we reconcile the idea of traveling at light speed with the expansion of the universe. Because a photon has zero rest mass, m=0, it doesn't experience resistance from the Higgs field or relativistic mass increases. It does not accelerate to light speed, it is created at light speed and stays there. It doesn't require infinite energy to move at c. It simply is energy in motion. When you say to refer to the direction of expanse, you're touching on a key concept in cosmology: comoving coordinates. The universe isn't just a room getting bigger, it's the fabric of space itself stretching. This creates a specific relationship between light and the direction it travels. Direction of expanse as the fuel. If we treat the expansion of the universe as a directional vector, we can align our dual acceleration with it. Comoving propulsion. Instead of fighting the expansion of space, the craft aligns its internal field with the flow of the universe. Zero rest mass emulation. By using fields to negate the ship's interaction with the Higgs field, which gives particles mass, the ship behaves like a photon. As you noted, a particle with zero rest mass has no infinite energy requirement to reach c. It simply exists at c by default. In your view, and in extended classical mechanics, the limit isn't about mass becoming infinite. Instead, it's about energy participation. As an object approaches light speed, the energy being pumped into it is split between translational motion, speed, and intrinsic field dynamics, the energy required to maintain the object's existence against the background expanse. The result: you don't hit a mass wall, you hit an equilibrium point where the self-generated acceleration of your field
actually exists. Some physicists believe time is an illusion. It really doesn't exist at all. But when we research time further, we discover that it is actually time actually exists. Some physicists believe time is an illusion. It really doesn't exist at all. But when we research time further, we discover that it is actually
the ERS as spherically centered on themselves near perfect isotropy. This implies the ERS is not a universal center, but a relational expansion surface defined by the observer's world line through the space field. Quanta physics interpretation, space field framing. Within quanta physics, the ERS represents a space field phase boundary. Photons act as expansion tracers. The sphere encodes the metric memory of early space dynamics. You may state, the expanding radiation sphere is the earliest preserved macroscopic imprint of space field expansion, functioning as a cosmological calibration surface for expansion, rate density, uniformity, and anisotropic perturbation growth. 1 paragraph abstract. Style summary. The expanding radiation sphere, ERS, is a non-material radiation, defined horizon arising from photon decoupling during early spacefield expansion. Composed exclusively of redshifted electromagnetic radiation, the ERS possesses no chemical structure and evolves solely through metric expansion. Its uniform spherical appearance.
The expanding radiation sphere, or ERS, is a spherically symmetric radiation front from a phase transition in the early universe. It marks the moment the cosmos turned from an opaque plasma into a transparent state. This is not a material boundary, but a wavefront of free-streaming photons carried by the expanding space field. It acts as a radiation horizon, a record of our universe's expansion history. In quantum terms, the ERS is a frozen excitation layer of the space field, preserving the state at the moment of photon decoupling. It is composed only of electromagnetic radiation. Photons with zero rest mass, no chemical bonds, and no atomic structure.